Okay. Today we're going to talk about how to name and write formulas for more chemicals. Today we're going to focus on the ionic compounds. And I kind of suggested yesterday that we were going to be working on two different types. There's more than this, by the way, in the chemistry world, okay? But we're starting basic. So probably the easiest thing is those molecular compounds we did yesterday. Why don't we just try a little test just to see whether you picked up on what we did? If I were to give you this compound here, you guys think we can name that? That is CCl3. So let's talk through it. The first thing right there is C is for carbon. Do I need to use a prefix if there's only one of them? No. Okay, so we call it carbon. Then after that, there's 3 of something. What's the prefix for 3? Yeah, okay. So you're going to call it a carbon tri. Now, we don't call it chlorine, though. We call it chloride. So this guy would be called carbon trichloride. Makes sense. Let's do a couple more here. What if I were to give you Ni2? This would be nitrogen diiodide. Because it's iodine, so it'd be iodide. Now, in both of these cases here, I started with something that begins with 1. What if I were to give you, let's try P3 or P2O3. Now that the first one right here has a 2 in front of it, you'd have to call it a di. Anybody know what P stands for? Not potassium. Phosphorus. Good. So you would call this a diphosphorus trioxide. This is a diphosphorus trioxide. Okay. Is everybody paying attention here? So, okay. That's one of the skills you need to have. Absolutely, yeah. Now, not only just be able to name them, but if I were to tell you, let's say I said that I wanted you to write a disulfur tetra oxide. Do you guys think you could write that one? This is actually the easier one for most kids. Di, okay, you need 2 of sulfur. Tetra, you need 4 of oxygen. So that's one skill I need you guys to have. That was really yesterday's focus. Okay. Today's focus is going to be another branch of naming things. These are chemicals that bond a little bit differently. Okay. And I want to go back to an analogy that I gave yesterday on how electrons work. Okay. So you want to buy something at the cafeteria. You want to buy a $6 special. But nobody has $6. Okay. I have $2 and somebody else has $4. And collectively, we share our $2 and $4, and we get up to $6. We've now gotten what we need, but we're sharing our electrons. That's a covalent bond. That would be like someone bringing 2, someone bringing 4, and we pool our resources. Okay. Well, today when we talk about ionic bonds, it's a little bit different. This would be a scenario where I have $7 and somebody else has $5. Now, my $7 is more than enough to buy a special. Right? If a special is $6 and I have 7, I have $1 left over. Make sense? Whereas my buddy only has $5. He's not quite there yet. But I'm really generous because I've got an extra buck, so I give it to him. You guys get where this kind of works here? Now here's the difference though. In this example here, everybody gets a special because my $7 buys me my special with $1 left over. My friend's $5 plus my extra dollar means he also gets a special. But it's slightly different. See the difference? In one example, you pool your resources and share. In the other one, what's going to happen is there's going to be a giving relationship. Sometimes I like to use this word. We call it a transfer, where someone's going to give their extras to somebody else, like your leftovers. That's how an ionic bond works. And I have to show you how that works in a picture format here. Before I get to the picture, though, I guess I threw in a slide here to remind you, this is the branch of how we're going to try to name things. Yesterday, we learned how to name things that are either called covalent or molecular compounds. Today, I'm going to first show you how to name something that's binary, and then eventually we're going to go down these other streams here. So here's a picture trying to represent what I'm talking about here. Here's a covalent bond. This is what we did yesterday. Now, it's all about electrons. The electrons are like in the last energy circle. We call that an energy level. Okay? And sometimes what they have to do is they have to share their electrons. If you guys can see in this picture right here, this atom right here had like 1, 2, 3, 4, 5, 6, and this guy had 1, 2, 3, 4, 5, 6. But collectively, they seem to both have access to these electrons right here. They're sharing them, right? They're both bringing one to the table. I believe this guy brought one electron, and this guy brought one electron, but now they both share them, if you can see that. Whereas like this electron right here only belongs to this guy. This electron right here only belongs to this one, but both of these electrons here, they both belong to both. That's the sharing kind of concept, okay, in a nutshell. But in an ionic bond, which is today's goal, there's more of like a, here, take my extras. You might notice in this one right here, see this first circle right here? That's not a valence electron because that's in like the first level. And you guys might remember how hydrogen and helium, see how they're at the top of the table there? That's why there's 2 electrons, because the first period has 2 elements in it. There's like 2 spots in it, right? But right here, in this open circle right here, there was like 1 extra electron. This guy had an extra one. But look over here, this guy right here. In his last ring, he had like 1, 2, 3, 4, 5, 6, 7. He's like got a lot of electrons. He just needs like 1 more to get there. This would be like, in the special analogy, this guy had $1 left over, and this guy over here needs $1. You guys gonna get that example here? This guy has like 1 extra electron that like is just out there floating around, that extra valence electron. Whereas this guy right here, there's like an open spot right here where he's like, I could use one, right? And that fitting together is the basis upon which ionic bonds form. And to help visualize this even more, I've made some manipulatives right here to kind of help show this concept. Okay? And it has something to do with charges. Today we're going to talk about positive and negative charges. But the basic idea is that if you have someone here that is positively charged and someone here that is negatively charged, if they have the right amount of charges, which are going to be your electrons, they can fit together. But if I were to take, like, say, this one right here, you guys see how, oh, that doesn't stick. Can you guys see how here I've put one that's a +2, and here I put one that's a -3, so it doesn't quite fit, right? But what we have in this scenario right here, the one that's on the board, is this guy right here has 1 extra electron. So I'm going to use this to represent 1 extra. This guy right here needs 1. Right? Can you guys see how, like, visually then it fits together just perfectly like that? That's our goal today, is I want to try to show you how these bonds are formed. So, but let me go through some of the notes first, just to try to build our way there. So, again, ionic compounds. Here's the main concept of ionic compounds. It's always formed between a metal and a non-metal. You guys remember in your periodic tables, I don't have one nearby, I should find one. Periodic table. Oh, here, I got one. Thank you, though. So if you guys have your periodic tables nearby, if you recall, yesterday we were working with covalent compounds, and those are only found over here as your nonmetals. Today we got to open up the whole periodic table, because obviously more than just these things form bonds. So today we're going to have one from column A, something from over on this side of the table, that's a metal, you need 1 of those. And then you need 1 from column B, a nonmetal. And if you have 1 of each of those, it makes the ionic bond. Now, what I'd like for you guys to do, if you could, is take a look at all of the metals, and I want you to focus on the charges. We haven't talked about this yet, but if you guys can see on your periodic table, often there's like a little charge listed, like say hydrogen is +1 or -1. Lithium is +1. Can you guys find those little charges in the top corner of your table? Let me draw out a square here. Let's say that you were looking at square number, let's keep it simple, 21. Number 21 is scandium. And one of the things that we're going to focus on today is up in this corner right here, scandium has a 3+ charge. I want to review what that means. Okay? Because obviously in a little while here, I'm going to now use this 3+ thing in correspondence with scandium. But we got to talk about, well, why is scandium a 3+ charge? And so if I could, I want to try to draw out what scandium looks like for energy levels. That thing's going to be in the way now. Okay. What number is scandium? It's number 21, right? So that means that in its nucleus, there are going to be 21 protons, because of number 21. Now, as an atom, it should have 21 electrons. I'm going to start drawing them out. The first energy level, how many elements are in the first period of the table? 2. Okay, so I'm just going to draw 2 electrons. Okay, we've used 2. Now in the next row of the periodic table, how many electrons are in that row? 8. Okay, so in the next circle here, I'm going to draw in 8 electrons. So 1, 2, 3, 4, 5, 6, 7, 8. Oh wait, 2 in the first row and 8 in the second row means we're up to 10. But this guy needs 21, so I better keep going. So let's use another energy level here. Oh, goodness, nothing's working today. It does this all the time. Okay. Wait, now look at the third row of your periodic table. So the first row has 2. The next row has 8. The third row actually also has 8. Okay, so let's draw 8 more there. 1, 2, 3, 4, 5, 6, 7, 8. Oh wait, how many are we up to now? 2 plus 8 is 10, plus 8 more is 18. But we needed 21. So from 18 to 21 means we need one more energy level, which this actually kind of makes sense. Scandium is in the 1, 2, 3, 4th row. Does that make sense? So there should be 4 energy levels. But how many electrons do we need in this 4th energy level? 3. Yeah, there's 3 remaining. Well, this would be like the analogy. Now that we got to upscale this, this would be like if you're trying to buy something that's worth, like, say, 20 bucks. This guy right here has $3 left over. Does that make sense? These 3 extra electrons are his extra money. He's got extras available. So what would happen if you had something extra and you were being generous and you decided to give away your excess stuff? If this guy gave away this electron here to someone who needed it, and he gave away this electron here to someone who needed it, and this electron here to someone who needed it, and he gave away his extras, just like your generous friend at the cafeteria, what sort of charge would this have? Well, there'd still be 21 protons, right? Because scandium is defined by its protons. But if there are 21 protons, and you got rid of 3 electrons, you only have 18 electrons. Does that not explain why there is a, I know it's not written on the board here, but why there is a 3 plus charge? That explains why scandium will often have a 3 plus charge, because he has 3 electrons to get rid of. And one of the things you might notice is that everybody in that same column as scandium, they're all plus 3s. Why are they all plus 3s? Well, because they're all the third one in. They all have 3 electrons they want to get rid of. Everybody in row 3 has 3 electrons to get rid of. So they're plus 3s. What about everybody in row 2? They're all 2 plus. Why? Well, they have 2 electrons to get rid of. Everybody in the first row is plus 1, because they all have 1 electron to get rid of. Okay. I want to show you one of those ones right here. If I can go up to the top here. Can you guys see this one? It's the same sort of thing I just showed you. It's sodium. Focus on this one right here. Okay, sodium. Before I even look at the table here, well, actually, let's do this. Look at the table. Find sodium. It's number 11. What's the charge on sodium? 1 plus. Let's explain why. Okay, so sodium has 11 protons. As an atom, it should have 11 electrons. So in the first little orbital right here, I put 2. Why is it 2, not 5 or 7? Well, actually, no. I mean, the first row has 2 elements in it. So 2 electrons go there. Then when you draw the second orbiting circle, you get as many as 8. And if you guys can see, there are 1, 2, 3, 4, 5, 6, 7, 8 in the next circle. But sodium is in the third row on the periodic table, which is why there are 3 orbiting circles. However, in its third orbiting circle, how many electrons are in it? Just 1, right? If sodium is supposed to have 11, 2 in the first, 8 more in the second, it needs to get to 11, it needs 1 more. But again, this is that generous friend. It needed a 10, and there's 1 left over, and it says, I don't need this extra dollar. Does that make sense? And so it's going to get rid of that electron and give it to somebody. And so if sodium were, say, to get rid of this electron, like you can see in the picture, and transfer it to somebody else, this sodium right here would now become sodium 1 plus, because it's now gotten rid of 1 electron. And when you lose an electron, you actually become positive. Does that make sense? So a lot of the periodic table ones right here, there's a very repetitive pattern. Take a look. Everybody in row 1 is plus 1, because they all get rid of 1 electron. Everybody in row 2, plus 2, because they get rid of 2 electrons. 3 electrons, 4 electrons. Even if you keep going you find that there's ones that do 5 electrons. Does that make sense? Actually, it's quite logical, hopefully, that there's like that pattern. But then here's the problem. If these metals over here are going to get rid of electrons, who takes them? Well, if the metal takes the electron, if the metal gets rid of the electron, it's the non-metals that take the electrons. And here's where this gets a little confusing, because you'd say, look at, say, like helium and fluorine and oxygen. Find me the charges. If you've got a periodic table, let me just draw a new one here. Yeah, it doesn't list the charges. For whatever reason, this particular periodic table, I'm just trying to draw a good periodic table here. I'm not doing very good at it. Right? If you were to look at all these guys over here, like say fluorine and chlorine and bromine, you might notice none of them have charges. So grab your periodic table. We need to write some of these in. Okay. And I've actually got some elements sitting up on the board here for us to look at. So I'm going to slide some of these ones over. But I want to point out a few things here, because I put these ones in rows. So if I could, if you guys look at these ones right here, here's everybody that was in group 1. And you might notice, if you can see from where you're at, all of these guys right here are all +1. Everybody in row number 2 is all +2. But the ones that we need to talk about don't have them listed. So I'm going to put a couple more rows up here. I've got a few here that are at like the back side of the table. So if you like slid these ones over, fluorine and chlorine are in a group, oxygen and sulfur, and nitrogen and phosphorus are. And I want you to look at the same pattern here. Look at this. Fluorine and chlorine, can you guys see that from where you're at? They're all -1s. Oxygen and sulfur are all -2s. And nitrogen and phosphorus are all -3s. I'm going to go back to my periodic table here and just kind of hold it up so you can see it side by side. Fluorine and chlorine are all in the second last group. So I know I don't have the elements that go below them, but bromine and iodide, these are all -1s. Oxygen, sulfur, selenium, tellurium, they're all -2s. Nitrogen, phosphorus, and arsenic are all -3s. Okay. Now I want to talk about why. So I need to, actually, remove this out of the way. Let's talk about why those have those charges. Is everybody able to write that down, though? Let's talk about why. I'm going to go back to this picture right here. You know how I drew one here of scandium? I'd like to draw one now of, say, let's go fluorine. So I'm going to draw a new picture of fluorine. So F for fluorine. Fluorine, if you can find it on your table, is number 9. So it means it has 9 protons, and it should have 9 electrons. So I'm going to draw it out. Here's a nucleus. It's got 9 protons in it. And then in the first energy level, as always, there's only ever 2 electrons. So 1, 2. Okay, second energy level. Now, fluorine is in level number 2, right? Here's the first level. Fluorine is in the second level. Let's add up. I need to get to 9. So 1, 2. Here's 3, 4, 5, 6, 7, 8, 9. So I've gotten my 9. But here's the problem here. How many electrons can go in this level here? 8. But how many are in the level? 1, 2, 3, 4, 5, 6, 7. There's an extra spot just sitting right here, just waiting for an electron. This is the person who doesn't quite have enough money. This guy right here, scandium, had 3 extra electrons just waiting there that it's not using. This is the person who has too much money. Well, chlorine over here, this is a person who's almost there. They have 7 of their electrons, and they just need 1 more. Well, if they can find someone to say, hey, can I have $1? You guys know this person in the cafeteria where they come up to everybody and go, do you have a dime? Do you have a quarter? Is there someone like that? That's what chlorine and fluorine are. Or they're saying, I'm almost there. I just need another 25 cents. Right? Does that make sense? Well, if fluorine, let's say fluorine finds that person that finally gives in and says, okay, fine, here, have $1. Right? And they pick up from somebody else an extra $1. Well, now look at them. Fluorine still has 9 protons, but rather than 9 electrons, they now have 10 electrons. And when they have 10 electrons, this now means that they have a -1 charge because there's more electrons than protons. Let me try another one. Let's try sulfur. Sulfur. So if you can find sulfur on your table, it's number 16. which means it has 16 protons and 16 electrons. Okay, so let's start drawing sulfur. Sulfur would have a nucleus. Here's a nucleus with 16 protons. With its 16 protons, it should have 16 electrons, so I'm going to start adding them up. Level 1, as it always does, has 2. Level 2 can have as many as 8. So I'm going to add them in 1, 2, 3, 4, 5, 6, 7, 8. I believe I'm now up to a grand total of 10. 2 plus 8 gives 10. I need 6 more, right? So open up level 3. Sulfur now opens up level 3. We need 1, 2, 3, 4, 5, 6. But your level 3 can hold 8, right? Look at the table here, right? The first level has 2 in it. The second level has 1, 2, 3, 4, 5, 6, 7, 8. But your third level can also hold 1, 2, 3, 4, 5, 6, 7, 8 as well. So it can hold 8, but we're only using 6. How many more does it need? 2. Which explains why if sulfur really goes around and begs and say, hey, you a quarter, you a dime, you a dollar, right? Eventually, if it can find an electron to go here and a second electron to go here, now it can get itself up to 18 electrons. And now it's full. Well, it's still sulfur because it's got 16 protons. But now what's the charge on sulfur? -2, because you have more electrons than protons. And now go back to what we just showed you earlier. Sulfur, if you guys can see, has a -2. Now, what we're going to focus on today now with those manipulatives is if you have someone with, say, a +2 charge and someone with a -2 charge, they can make a bond. Does that make sense? Because really what happened in this scenario here is the +2 person has 2 extra electrons. The -2 person wants those electrons, so basically the electrons, I say, oh, here, have my 2. And the other person's like, sure, sweet. That idea there? And that's what forms what's called an ionic bond. That's the basics behind it. Now, if you can understand that, that's fantastic, because then you'll really, hopefully, internally be able to picture what's happening. But if that was still a little bit fuzzy, that's actually not really the end of the world. My main goal now, though, is can we just name them? Okay, like if you internally get that, that's fantastic. But I got to be honest, I got grade 11 students who still kind of are working on wrapping their heads around that. More importantly now, can we name these things? So, okay. Here I just had a slide that I just wanted to use to show you guys that everybody in this column right here was -1. Everybody in this column right here, if you can see it, there's a -2 in that column. By the way, I should talk about this. I haven't mentioned this very last column right here, helium, neon, argon. We call them noble gases because they don't react with anybody. They were so snooty. They were like the nobles that wouldn't hang out with commoners. They don't react. We can actually explain this. These guys right here have no charge. And the reason why is it's because they're completely full of electrons. If we were to draw these guys, that's full by the way. If we were to draw these guys as energy level diagrams, their orbitals are completely filled. They have no reason to need any more or to get rid of any. Does that make sense? That's actually why they're at the end of the table. As we read along, this guy has 1 extra, 2 extra, 3 extra. As we go along, we finally get to the point right here where these guys are filled up, so they don't actually react. Let me draw one of them. I'll draw neon, and then I'll move on here. Neon is number 10, which means if I drew this out, neon would have 10 protons. I'm going to draw the first energy level. First energy level should have 2, 1, 2. The second energy level should have as many as 8. So 1, 2, 3, 4, 5, 6, 7, 8. Hang on, 2 plus 8 is 10. We're filled up. All 10 electrons have been accounted for. Does neon need any more electrons? Does it have too many? This would be the person who they brought exactly $6 for the special. They don't need anything. They don't have extra. They're exactly good to go. So they don't react with anybody. So anyways, all this being said, I need to get to my eventual point here, which is that we need to be able to name these and write them out. So here's the slide I want you guys to find here. If you understood the internal, like, why this works, that's great. But sometimes it's just okay to know how to do it rather than why it works. So So this is the real key point here. We need to be able to name these things. This is actually even easier to name, believe it or not, than the previous system. There's actually less to do. You know how we used to use di and tri and tetra and all those prefixes? We don't do that. We literally just say, we look at what's written there, and we just call it what's there. For example, I've got Ag and Cl. Okay, Ag is silver, Cl is chlorine, so we just call it silver chloride. You still change the ending to "ide." You still change the ending to "ide," but like there's no dis and tris and tetras, you just call it as you see it. For example, this one here, K is for potassium, O is for oxygen, so you just call it potassium oxide. And here, Al is for aluminum, S is for sulfur, so you call it aluminum sulfide. Now, the first question some kids would have is, hang on a sec, Chris, why is there a 2 sitting down here? Or a 2 and a 3 sitting here? Right? Well, it's because there's 2 of them, and I want to show that now with manipulatives. I'm going to do potassium and oxygen, and I've got them sitting here. Here is potassium, K, and here is oxygen. And if you guys can see these, or you either remember their charges, potassium is +1, but oxygen is -2. And I'm going to grab my manipulatives. So I need a +1 and a -2. Why is potassium +1? He has $1 extra. Okay? But oxygen has -2, which means he needs $2. So if potassium gives his extra 1 to oxygen, that's great. You can see how this little indent has been filled in, but is oxygen all the way there yet? Oxygen still needs to find another person to badger money out of. But this is where it's brilliant. What if we didn't just have 1 potassium? What if oxygen went to this potassium and said, here, give me your electron? And he went to a second potassium and said, hey, you also give me your electron. Now there actually are 2 of these guys right there, which is why there's 2 potassiums there. And so if you can visualize how this fits together, now this explains why you need 2 potassiums for every 1 oxygen. And I want to try a few more of these examples to try to help you. So the next one I have is aluminum and sulfur. And I have sulfur right here, but I don't think I have a card for aluminum, so I brought a spare one that I can write on. So here, I'm going to put aluminum there. So I need your guys' help. Go to your data booklets, find wherever aluminum is, and see what charge it has. We have to know what charge aluminum has. Can you guys find that on your table? Aluminum is number 13. 3 plus? Can everybody else find that? Aluminum is a 3 plus. So here's what this means. If aluminum is a 3 plus, he has $3 extra that he can give away to somebody else. But sulfur is a 2 negative, which means he needs $2. So if we grab these manipulatives, you're going to see they won't fit. Here's a 3 plus, here's a 2 minus. Aluminum, if you look at my manipulatives, has 3 extra prongs. Does that make sense? He has 3 extra electrons he can give away to somebody else. Sulfur needs 2. Well, if I try putting them together, you might think, well, actually it works out well because sulfur got filled up, right? But aluminum actually still has an extra $1, right? Of the 3 that he had, he gave 2 of them to this guy here, but he still has 1 left over. So it doesn't really fit. But if we start playing around with how many of each we have, watch this. What if I use a second sulfur? Okay, well now I've got 1 aluminum and 2 sulfurs, but it actually still doesn't fit yet. So what if I were to grab a second aluminum? Still doesn't quite fit. What if I were to grab a third sulfur? Can you guys visually see how this all fits now? What we really need is 2 aluminums, each bringing with them $3 extra. 2 times 3 right here would give you a grand total of 6. So there's $6 extra here between the 2 aluminums. Then sulfur, each sulfur needs 2. So you need 2, you need 2, you need 2. If it stays, whatever, it won't stay. 2 times 3 is also 6. So at the end of the day, in order to make this fit, we need to have 2 aluminums for every 3 sulfurs. And that's how you write its formula. Now, this is a little bit challenging at first because not only do you need to know all of the charges, but you have to figure out how to make them fit. So I really recommend we need to practice this because it's not one of those things that you just look at once and go, I got it. You might, but you probably want to try it a few times. So I believe I have some examples here. Why don't we try some of these examples? Okay, so let's start at the beginning here. We're going to do sodium and chloride. So the first thing you might want to do is figure out, well, what's the symbol for sodium? What's the symbol for chloride is chlorine. So sodium is Na, and chlorine is Cl. But the real question is, how many of each do I need in the bottom corner? So I'm not going to go to the board and grab manipulatives anymore if I can avoid it, because I want to try to move past that. What I need you guys to do is go to your table and find me their charges. What is the charge of sodium? What is the charge of chlorine? So sodium is +1. Often kids will write it above it and say that's +1. Chlorine's -1. Now, if I can avoid going to the board here, if you have a guy that's a +1 and a -1, do we need to have like 2 or 3 of them, or can they just fit together perfectly? They fit. So, I mean, in theory, you could say, well, I just need one of these for one of these, but we don't even write ones. So the formula for sodium chloride is literally just NaCl. And you guys might have known that because that's salt. Now, the only thing I ask is that when you're done, though, just erase the charges up top. Just use that to kind of help you figure it out. But you can probably erase them when you're done. So this is your formula, NaCl, a compound. Now, that first one's pretty straightforward, but let me try a new one here. Let's try aluminum and chlorine. Okay, so aluminum's Al, chlorine is still Cl. Okay, this one I'm going to go to the board for, though. Aluminum I just wrote, didn't I? Here's aluminum. It is 3+. Chlorine is -1. If I were to go grab some of these manipulatives, if I can find one, here's the 3+. Aluminum has 3 spare dollars it doesn't need. Chlorine can use one of them. Does it fit? So this is what I need you guys to be able to do, though. You need to be able to get away from manipulatives at some point and be able to figure out, well, how many of each do I need? And the answer is I need 1 aluminum, but if I were to have 3 chlorines, if I'm just going to draw in what's here, if I were to have a second chlorine go there and a third one go there, can you guys see how this would now finally fit together? So we need aluminum once, we need chlorine 3 times. So the formula is AlCl3. Now, I don't call it aluminum trichloride. The tris and dis and tetras only apply to both things being nonmetals. But since aluminum is a metal, we have a different naming scheme. Okay, I'll just move this out of the way and we'll try another one here. Like I said, this is the thing you need to practice. If you don't practice this, it's really hard to get better. Okay, so let's try calcium and nitride. So first step, calcium is Ca, some of you are ahead of me. And then nitride is going to be based on nitrogen, which is letter N. But that's not really the important part. The important part right now is we got to figure out what their charges are. So if you can look at your table, what's calcium's charge? Okay, +2. And nitrogen is, I believe we wrote it down earlier. Nitrogen is -3. Okay, positives and negatives totally fit together, but these ones, you got 2 versus 3, you don't have enough. I want to show you a little shortcut, by the way. 2 and 3 in math, you guys might have learned about something called the lowest common multiple. You ever used that phrase before? 2 and 3, okay, well, quick tutorial. In math, a lowest common multiple would be like if you had the numbers 3 and 5, that would be 15. Because 3 goes into 15, 5 goes into 15. Okay. If I were to give you the numbers 4 and 3, the lowest common multiple would be 12, because 4 times 3 gives you 12, 3 times 4 gives you 12. Anyways, if you've heard of this before. 2 and 3, the lowest multiple of that would be 6. So I got to figure out, how do I turn this 2 into a 6? Well, I need 3 of them. And how do I turn this 3 into a 6? I need 2 of them. Some kids all of a sudden then realize there's a pattern here. This 2 right here essentially goes there, and this 3 right here goes there. And you can use that same logic on almost every other compound. This was a +3, this was a -1. This 3 goes there, this 1, we didn't write it, but it goes there. This one was a 1. That one was a 1, which is why there's 1s in both spots. Once you figure that out, it actually is a lot faster than you'd think. In a way, yeah. So if you're ever asking your math teacher, when am I ever going to use this? I've got a spot. Now, I can do more examples of this if you guys would like, because kids are at various different levels. Some kids will be like, I got it, Chris, I'm good. Other kids are still like, okay, so I understand you're at different levels here. If you need more help, one of the things I want to encourage in you guys is advocate for your help and call me over later and I'll try to help do more examples. Okay. But in interest of time, I do want to move on here because we got more than this today. Now, if I give you the other way of doing things, if I give you a chemical formula, it's actually even easier. All you have to do is just name what you see. So like for this one here, KBr, K is potassium. It's odd. It's actually from the Latin one. I know P should be for potassium, but P is actually phosphorus. So you just call this one potassium bromide. You just change it to "ide" at the end. Be is beryllium. And then O changes from oxygen to oxide. Sr is for strontium. And then F is fluorine. You just change it to fluoride. So when you're going from the formula to the name, you don't even need to worry about the charges. Just literally look at it and just name what's there. The harder one, though, is if I give you a name and you have to give me the formula, because then you have to know your charges to make it properly. That's all. So my advice, though, practice, okay? Don't just watch this once or twice. Just practice, okay? And you're only going to do like 1-ratio ones. Like we won't do 3s and 2s and stuff like that. So, okay. Okay, here's one more picture just to try to re-illustrate the concept of sharing versus transferring, just to make sure that's clear. If it's covalent between nonmetals, this guy has an extra electron, this one has an extra one, and they both say, hey, let's share our electrons. So your extra and your extra, they both come together and they share those two. That's sharing. But today what we're talking about is someone who has an extra, and this guy right here could use one. This one needs one. So this one will literally give his electron away in like my money scenario. Okay, on this slide right here then, we don't have time to go through all of these today, but I would really recommend, you should practice this. Okay. So why don't we try just doing like say 2 more each, and then can I leave the rest of this for you guys to try as you feel you need to? So let's try 2 more though. The hardest ones are where I give you the names and you have to write the formulas. So why don't I just pick a few out of this column right here, and we'll name a few of those. For example, let's do this one here, strontium oxide. Let's try that one. If I asked you guys to write the formula for strontium oxide, first step, I need to know what strontium is. And sometimes it takes a while to find it. Okay, so it's number 38. It's Sr. And Courtney, you're right, it's a 2 positive. Good job. Okay, then oxide is from oxygen. It's number 8. And it's a 2 negative. Now, I just want to point out a common mistake that kids might make. Some kids, once they learn that crossing over method, might think that you put a 2 here and a 2 here. We don't actually have to do that because it like reduces. Like 2 and 2 can really reduce to being just 1 and 1. So don't always use the crossover method because you just need one of these for every one of these. So your formula is just literally this, SRO. 1 strontium, which gives to 1 oxygen, which takes 2. It's perfect. It just fits. Let me try one last one and then we'll move on. Let's do sodium sulfide. So sodium sulfide. Sodium is number 11. It is Na, and it is a +1. Sulfide refers to sulfur, which is a -2. Do these guys, quote unquote, fit? Okay. Just use the crossing over method. This 1 right here goes there. This 2 right here goes there. And then just use an eraser here. We don't need the charges anymore. And we don't bother writing a 1. Sodium sulfide is Na2S. 2 sodiums for 1 sulfur. Okay, so I do want to move on. I get that some people are going to be at different levels here. So like, if you get this, that's fantastic. You may only want to practice a few of them. But I really strongly recommend, I can't say this enough, if this is something that you're like, ooh, I didn't get that, you need to practice. Just like you might want to practice your parallel parking. No. Because when you guys eventually take a driver's test, they're going to make you parallel park. You probably should try it once or twice. Well, you guys you guys will be tested on this, not just from me though, but like this is on the PAT. So I'm warning you, you're gonna want to try this. Okay. Oh wait, I want to move on though because I have a slide right here. It was way back here where we have to talk about different ways of naming things. Now I've covered most of the key stuff, but right now we've only talked about binary compounds. We give the name binary because literally there's only two pieces to it. But I've got to talk about two more streams here, and it's not overly difficult, but I need to get to that as well as to how to name even more challenging pieces. So, okay, that being said, before I get to those pieces here, I actually have some properties. Okay, so I know I'm jumping around here. Can you guys find this slide here? I jump around like crazy. This is why I give you notes so that you can just search until you find them. Okay. Last day, I gave you guys some properties of molecular compounds. I believe they have a low melting point. I believe they were brittle or something. I think it was that they were chemically easy to break up, something like that. Is that the word we gave? It was in this. Well, let me find the slide here. You guys stay on this slide. I'll go back a ways. Weak crystals. That's what it was. Yeah, it was these slides here. They had a low melting point. They have weak crystals, and they do not conduct. Those are some properties we learned about molecular compounds. Well, the cool thing about ionic compounds, as I scroll back to here, is that they basically have the exact opposite properties. Ionic compounds actually have a very strong shape to them. So they actually have a high melting point. Most of these things are solid. And one of the cool things about them is unlike them having a weak crystal, these guys actually have a very strong crystal shape. Literally, if you were to break one of these things in half, it doesn't like shave off like ice does. It would literally like cleave into two pieces. Like for example, if I were to take this sheet of paper here and rip it in half, these two pieces don't just like disintegrate. Does that make sense? As soon as I break it in half, they don't just like fall apart. Right? That's what gives it a strong shape to it. Whereas covalent stuff, if you try to break it, it would like just all just like crumble, like a sandcastle or something like that. That makes sense? Okay, and then the other properties I've got listed here that you should know is that these things are usually soluble in water. What it means is that these guys dissolve. If we're talking about a compound that dissolves, it's usually ionic. And I can explain why. Ionic compounds are made out of positive and negative things. And in water, we can actually separate them, which is why they conduct. Because these things have positives and negatives, they can conduct electricity. But if we were talking about covalent compounds were only negatively charged things. And there's no positive to be like the yin to the yang. Like you need to have both positive and negative to dissolve and to conduct electricity. So, long story short, I just need you to know these properties. Okay. So, ionic things are strong. They have high melting points. Covalent things are weak. They're usually gases. Ionic things conduct because they dissolve. Covalent things don't dissolve and don't conduct, basically. They're just opposites of each other. I just got a picture here just kind of showing how a conductivity tester works, but I think I can move past that. Here's a slide that just talks about the idea of solubility. I only have this slide in here just for one reason. It's this right here. If you ever see this little prefix, this little subscript here, AQ, has anybody ever seen that one before? Okay, you will as we go along. This little AQ stands for the word aqueous. It means that it dissolved in water. There's actually 4 states I need you guys to know. There's solid, liquid, gas, so S, L, and G. But if I ever show you AQ, it means that we took that and we dissolved it in water. And it's now aqueous. That's all. So that's the only reason I throw the slide on here is just so that if you ever see this, now you're not surprised and wondering, what does AQ stand for? So it just means it's an ionic substance that's now been dissolved in water. Kind of like if you were to take like some Kool-Aid crystals and dissolve them in water and make Kool-Aid. you would say that it is aqueous. That's all. Okay, and that's kind of what I got here is just the same concept. Don't forget that sometimes we're going to put a little state of matter afterwards, G, L, and S. So again, G for gas, L for liquid, S for solid. Okay, I need to show you two more branches off of that naming thing tree. So I've already shown you binary compounds. There's two more little twists you need to know. If you guys have a periodic table nearby, I'd like for you guys to go look for chromium. Chromium is number 24. Can you guys find chromium? It's number 24. There are some weird anomalies to the periodic table that I'm not even sure that I could fully explain to even my grade 12 kids, let alone you guys when we're starting in grade 9. But here's the basics, okay? There are some elements that have more than one charge. It's very strange. But if you notice here, can you see how chromium has +3 and +2? There are a lot of elements in the middle of the table that have more than one. Like chromium is 3 and 2. Next to it, manganese is 2 and 4. Iron is 3 and 2. Cobalt is 3 and 2. Nickel is 2 and 3. Copper is 2 and 1. We call these things multivalent elements. And like I said, I'm not even sure I can explain to you why they happen at this point. So if you can just accept that, okay, cool, there's some things that have more than one charge. That probably works for now. What was that? Okay. I mean, if you'd like me to try to explain why there's more than one charge, I can do that later if you'd like. But right now, I just need to accept there's some things that have more than one charge. This makes it really confusing because we have to know which charge we use. So what we do is we use Roman numerals to tell us which version of the ion there is. So I want to talk about this compound here. This is chromium and sulfur. Normally, this would be the easiest compound to name. We would just call it chromium. And then sulfur would be sulfide. However, because chromium can either have a 3 charge or a 2 charge, I have to right here put a Roman numeral telling you whether it's the 3 or the 2 that we used. So we kind of have to work backwards here. What's the charge on sulfur? Sulfur is actually, if you look it up, sulfur is actually a 2 charge. Sulfur is 2 negative. Now I want to present to you two options here. This could have been chromium 3 plus or 2 plus. We have to figure out which one it was. So I'll go grab the manipulatives again here. Sulfur is a -2. So here's 1, 2, 3 -2s. And we either need +2s or we need +3s. Okay, so hypothetically, let's say it was the +2. Would that have fit? It's not the +2 then. Does the +3 fit? Okay, so here's what that means. We just have to make one subtle change. If there is more than one charge, right here in brackets, we would put the Roman numeral 3 and tell you that it was chromium 3 sulfide. Okay. You're not going to do a lot of this, but I have to warn you that on the PAT, though, I have seen questions where they put chemicals with Roman numerals. So I want you to be aware that, like, if you see this Roman numeral right here, that's what it's referring to. It's telling you that this item right here has more than one charge. It's telling you which one it is. It will be, yeah. They put this on the PAT. Okay. Now, it's not that bad if you remember to look and double check and see, is there more than one charge? If there's more than one charge, you just need a Roman numeral here. So let me try one more example here. I'll do a new slide. If I were to give you the compound FeO, normally when you name it, it's really easy. You just name it as iron and oxide. However, if you look carefully at iron on your table, iron is number 26. You guys will see that iron actually has 2 charges, 3 or 2. So in this location right here, you're either going to put a 3 or iron. You're going to put a Roman numeral 2. We need to figure out which one to put there, the 3 or the 2. So you have to kind of like work backwards. Start with oxygen. What's oxygen's charge? Okay. So if oxygen is a -2 charge, then iron here, in order to fit, better be the +2 charge. So we needed it to be this one, iron 2 oxide. That's all that happens. You don't change a lot more, and it only applies if there's more than one state. If I were to give you this compound here, MgO, you would call this magnesium and oxide. Oxygen is -2, which means magnesium better be +2. But we don't bother writing a Roman numeral because if you guys look on your table here, magnesium only has a +2 there. So like if there's only one charge, don't bother writing a Roman numeral. But if there is more than one charge, you need a Roman numeral here. So this one right here would just be magnesium oxide. Don't bother because there's only one charge. So it's a little bit of like an extra twist we throw into things. Like I said, this is not the main focal point of what we talk about in this course, but it will come up. So don't be surprised and be like, what the heck is this Roman numeral here? Hopefully, like hopefully you'll be able to follow along. Okay. So, and then there's one more twist I need you guys to know about. These things are called polyatomic ions. Okay. And again, at first, people are like, oh my goodness, Chris, this is too much. Okay. Bear with me. Okay. Sometimes we have chemicals that look like this, CaCO3. This is a compound, but rather than having 2 parts to it, there's actually 1, 2, 3 parts to it. That's all. Well, there's a way that we deal with that, and it's called a polyatomic. There are certain things that can actually be like in a group together, hence the name polyatomic. And all of these are found in your periodic table. There's usually like a little open space right here. There's a little chart up there. Can you guys find that chart? It says Table of Common Polyatomic Ions. In that chart, you might notice every single one of those things there has both a charge in the corner and has more than one element in it. We call those polyatomics. In this example I just showed you right here, CO3 is like a collective group. And if you can find CO3 in that chart, and by the way, I know it's blurry, so I'm going to give you guys a new printout of one that's not blurry so that you can see it better. But if you can find a CO3 in that chart, this thing is called a carbonate. Okay. Now, it's actually, these ones are the easiest ones to name. All you have to do is just write what you see again. So Ca stands for calcium. This CO3 as a whole unit is called the carbonate. So we call this thing calcium carbonate. And this is how we deal with items that have more than 2 elements. Because you guys might see something that has 3 or 4 elements in it. So let me show you a couple of examples and then we're done. Okay. Here is one. It's MgSO4. You might notice that this is not binary. It doesn't have 2 things. There's an Mg, there's an S, and there's an O4. One of these things is a polyatomic. So we would want to look in our little table here and find, say, like what an SO4 is called. And if you can look up top in this little column here, I know it's blurry, but it's in the 3rd row over, 5th one down. SO4 is called a sulfate. So therefore, this thing is not called a magnesium sulfur oxygen. Some kids think that's what you call it. They say, call it a magnesium sulfur oxide. All of SO4 is known as a sulfate, so you just call it magnesium sulfate. Okay. Right here, we already did this one. CO3 is a carbonate, so you call this barium carbonate. So, by the time we're done now, if I go back to this slide right here, I need you guys to be able to, not only just for my test, but on the PAT, be able to follow this flow chart. Okay? Guaranteed, no doubt, you guys need to be able to name what we did yesterday, the covalent molecular stuff. Okay. And guaranteed, you should be able to do binary stuff. You're not going to be tested nearly as much on this, but like if I give you something like this, lead 4 sulfide, you shouldn't be like all of a sudden like, why is there a Roman numeral there? Okay. Hopefully I've now explained to you the reason why there's a Roman numeral is that if you look at lead actually has more than one charge, so the 4 tells you the charge. Okay. And if I were to give you a compound like this, NH4 in brackets 2 CO3, this shouldn't throw you so much because now you're going to think, well, this isn't binary anymore. I need to look in my chart at the very top. And if you were to look up NH4, NH4 is known as an ammonium. And if you were to look up CO3, CO3 is known as a carbonate. And so you just literally name it as you see it. No special rules to those, but you have to be aware that a compound is not just 2 things. It could be 3 or 4 or 5. So, It's a lot, hey? It is. So I've got some last examples. If you guys can stay with me for like say 5 more minutes here, why don't we try some last examples? And then we'll call it a day. But this really is the sort of thing now that you need to practice. Okay, I've given you the theory on it, but I don't know, just like with driving or volleyball or playing piano, whatever, like you got to try this, right? You got to practice. If I can give you guys some advice, what I really want to encourage is on my learning cycle there. I've now given you some knowledge, hopefully. You now need to apply it, but don't forget the last step. Get feedback. Try it and then call me over and say, hey, Chris, can you look at this and make sure I got it right? Or say, hey, Chris, can you help me with this? I'm still not getting it. Because it's fine to not get it yet. Right? That's the key word. You don't understand it yet, but like we'll keep working. So let's try one here. This one here is NaClO4. Right off the bat, this one's odd because of the fact that there's like 3 elements here. So what we need to do is we need to figure out which one is the grouping. And if you look on that little chart there, a ClO4 is on this top chart here. It's down in like the bottom right-hand corner somewhere. ClO4 is known as a perchlorate. Can you guys find that? I know I'm pointing to a really small thing right here, but look in the first row, the fourth one from the bottom, ClO4 is called a perchlorate. So here's how you name it. You call it sodium, oh goodness, sodium perchlorate. That's it. You just name it as you see it. There's nothing special to it. All you have to do, though, is just recognize which one the polyatomic is. Let's try this one here. Sr is strontium. But we got to figure out what an SO4 is. So again, you need to use your table and search until you find an SO4. So I'll give you a second. Try to find where SO4 is on there. SO4 is in the 3rd column over, 5th one down. Again, I'm sorry it's blurry. Can you guys find that? 3rd column over, 5th one down, SO4. It is called a sulfate. You guys find that? Okay. So if you can recognize that SO4 is a sulfate, you just call it strontium sulfate. I'll do one more here, and then I think we'll call it a day. Ca, and then this whole NO3 is in brackets twice. The reason for that is due to the charges. Calcium's actually +1. This guy's -1, so you need 2 of the whole thing. But that doesn't matter for naming it. Okay. Ca is calcium. We just need to find what the heck an NO3 is. So again, just search on the table. Until you find NO3. By the way, they're kind of alphabetical, so that helps a little bit. They're not perfect, but they're not bad. NO3 is right in the middle of like the entire thing. It's called a nitrate, yeah. So that's all you do. You call it a calcium nitrate. That's it. So although polyatomics look confusing, it's actually really straightforward. Literally just find what it's called, and you don't even change any names. You just name it as you see it. So, okay, why don't I call it quits here? Because I feel like you guys have had a long day. Here's what we need then. Tomorrow's a work day. You guys got to practice this. So either on your assignment or maybe like on this slide right here, try some of these now. Okay? Get some feedback, but see whether you can do it yourself. Okay? We're basically done the unit, by the way, guys. Like this is like one of the last major things we do. Okay, I'll stop the video recording. If you guys want to go take like a quick stretch, go ahead. That's a long lesson.